Good afternoon, everyone. Myself is Srijita. Today we are going to start the 10-week live session of the chemical process technology. In this lecture, Sarah has talked about the carbonylation process, the hydroformylation process, and ethene oligomerization. And we will do the assignments or questions answers around that. And I will be starting in 5 minutes. Let's just start the session. I hope the screen is visible. So the first question is, methanol carbonylation is an exothermic process. Is it true or false? Methanol carbonylation is an exothermic process. True or false? The answer is true. Methanol carbonylation is an exothermic process. Exothermic means it produces heat. Right? Next question. Why is methanol carbonylation reaction occur at high pressure? Why is methanol carbonylation reaction occurred at high pressure? So methanol carbonylation is an exothermic process you have just seen. And now methanol carbonylation can occur at 10 bar, 30 bar, and even in 300 bar. Right? That means it can occur at high pressure also. Right? Even in the low pressure, the conversion is achieved or conversion is high, right? But still, why do we have to use higher pressure, that is 300 bar? At high pressure, the reaction mixture can be retained in liquid phase. Okay? It can be retained in liquid phase. And also, the catalyst can be developed and maintained in active form. That means it will not decompose at high pressure, but at lower pressure it might decompose. Then if catalyst is decomposed, then what is the point of doing the reaction, right? So for these two reasons, the mixture is kept at liquid phase and the catalyst can develop its active form in the high pressure. That is why we have to maintain this methanol carbonylation reaction at higher pressure, even if at the small pressure the conversion is achieved. Okay. Next question. In methanol carbonylation process, catalyst complex is not very stable at high carbon monoxide pressure. Is it true or false? In methanol carbonylation process, catalyst complex is not very stable at high carbon monoxide pressure. The answer is false because we have just seen that catalyst complex can be stable at high pressure only, right? So not stable at low carbon monoxide pressure. So here it is false. Okay. Next question. In which form iodide is available in methanol carbonylation? In which form iodide is available in methanol carbonylation? So iodide is an important part of the catalyst. So this iodide is available in which form? The answer is hydrogen iodide. So iodide is part of the catalyst and it is available in the hydrogen iodide form. Okay. Next question. Explain the complete methanol carbonylation Monsanto process. Explain the reactions involved in the methanol carbonylation Monsanto process. So the first reaction is methanol reacts with the hydrogen iodide that we have seen just that it is the part of the catalyst, and it produces methyl iodide, right? That is CH3I plus water. So it is an exothermic reaction. That means it is producing heat. Okay. Now the second reaction is this CH3I will react with the carbon monoxide. That is, the carbonylation will happen in the second step. Okay. So now the carbonylation will happen and it will form a complex, that is CH3COI. And it is also an exothermic process. Okay. Third reaction is this CH3COI methyl carbon monoxide iodide complex will again water with the previously produced water, and finally it will produce our desired product, that is acetic acid and hydrogen iodide, which is regenerated as in the form it was given into the reaction, right? So HI is now regenerated or separated, and it is also an exothermic process. So these three equations are the equations involved in the complete methanol carbonylation Monsanto reaction. Okay. So you have to be very careful with these equations to remember. Next question is, what is the dependence of the reaction rate of rhodium-based methanol carbonylation? What is the dependence of the reaction rate on rhodium-based methanol carbonylation? That means this Monsanto process, methanol carbonylation, where rhodium is used as catalyst. Okay, rhodium is used as catalyst. So that is why I have called it rhodium-based methanol carbonylation. The answer is it is independent of reactant concentrations. That means the reaction rate is independent of the reactant concentration. That is, if you check out the slides, you will see that rate of the reaction is K, that is the reaction constant, concentration of rhodium-based catalyst, and concentration of the methyl iodide. Okay, so it is not dependent on the concentration of the reactants of the reaction, that is methanol and carbon monoxide, right? So that is why it is told that independent of reaction rate is independent of reactant concentrations. Next question, what is the order of the rhodium-based methanol carbonylation reaction? What is the order of the rhodium-based methanol carbonylation reaction? Hello, am I audible? Yeah. So there is a connection mistake, that is why I have to restart it. Okay, so what is the order of the rhodium-based methanol carbonylation reaction? What is the order of the rhodium-based methanol carbonylation reaction? I hope my voice is audible now. So, In the last question we have seen that it does not depend on the reactant concentrations, right? It does not depend on the reactant concentrations. So that means it is a zero order reaction. So when some reaction rate does not depend on its reactant concentration, it forms a zero order equation. Okay, so it is zero order. Next question. In methanol carbonylation process, output rate remains constant regardless of the level of conversion. In methanol carbonylation process, output rate remains constant regardless of the level of conversion. Is it true or false? The answer is false. The answer is true. Sorry, 1 minute. The answer is true. Okay, so the in methanol carbonylation process, output rate remains constant regardless of the level of conversion because it does not depend on the reactant concentration, and that is why it is a zero order reaction. Okay, so same question here, the answer is true. Next question. What is the structure of the catalyst for the methanol carbonylation Monsanto reaction? What is the structure of the catalyst for the methanol carbonylation Monsanto reaction? So, the methanol carbonylation Monsanto process uses rhodium based catalyst, right? So, its structure is RHCO whole to I2. So here RH, then here it is CO, here it is CO, here it is I, here it is I. Okay. So this is the structure of the catalyst used in Monsanto reaction. Next, in methanol carbonylation Monsanto process, methyl iodide reduction process is the rate determining step. Is it true or false? Methyl iodide reduction process is the rate determining step. Is it true or false? So it is false because the methyl iodide oxidation process is the rate determining step. Okay. So it is false. Next question. Next question. What is the structure of the acyl complex? What is the structure of the acyl complex? So the acyl structure of the acyl complex is CH3CO. Okay, this is the acyl complex structure. Next question. What is the catalyst used in methyl carbonylation Cativa process? What is the catalyst used in methyl carbonylation Cativa process? What is the catalyst used in methyl carbonylation Cativa process? So rhodium-based catalyst is used in Monsanto process. Okay, right? So our answer is iridium-based. Okay, so in Cativa process we use iridium-based catalyst. Next, oxidative addition of methyl iodide is faster in case of Cativa acetic acid process compared to Monsanto process. Is it true or false? This is false. This should be true actually. I have done it mistakenly. So the answer is true here. Okay, because methyl iodide, that is CH3I, is the chemical which reacts with the which make which makes complex form with the catalyst. Okay, so in Monsanto process the catalyst uses rhodium based, but in the Cativa process it is iridium based, right? So in Monsanto process the catalyst is rhodium based, and in Cativa process the catalyst is iridium based. So oxidative addition of methyl iodide to this iridium catalyst is much faster than in the case of the rhodium based catalyst, that is in the Monsanto process. So from that line we have to understand that it is true. So in Cativa it is Cativa means the iridium catalyst and Monsanto means the rhodium catalyst. Okay, so it is true. Next question, which one is not the inactive form of catalyst in Cativa active acetic acid process? Which one is not the inactive form of catalyst in Cativa acetic acid process? Which one is not the inactive form of catalyst? The right answer is this. Okay. So the structure is just similar to the previous one. CO, CO, I, and I. All the other forms are inactive form. Okay. Next question. What is the physical condition maintained at reactor in Monsanto acetic acid process? The answer is 450 Kelvin and 30 bar. So this is the condition maintained in Monsanto acetic acid process in the reactor. Next question. What is the vent gas in Monsanto acetic acid process? So the vent gases are carbon dioxide and water, steam, right? So these are two the vent gases in the acetic acid process. Next, what is the function of the flash vessel? What is the function of the flash vessel? हाँ हाँ बोलिए हाँ हाँ कर दूँ 3 मोबाइल क्या नहीं अभी कर दूँगी हाँ हाँ ठीक हाँ 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 ठीक अच्छा अच्छा ठीक है ठीक है नहीं आ रहा है हेलो हाँ नैनो में हाँ आप उसमें नैनो के इंग्रेडिएंट्स में रख देंगे क्या जस्ट वहाँ पे रख के बोल दीजिए कि थर्ड थर्ड फ्लोर में है आके लेगा ऐसा कुछ भी फिर दे दो So, what is the function of the flash vessel? This is the vessel is used for separating the liquid and the gas phase. Flash vessel is used for separating liquid and the gas phase. Okay. Next question. What are the light column products in acetic acid Cativa process? What are the light column products in acetic acid Cativa process? So the light column products are methyl acetate, methyl iodide, and some portion of water. Okay. So these are the light column products in Cativa process or methanol carbonylation process altogether. Next, what is a product of the dry acetic acid? What is the product of the dry acetic acid? What is the byproduct of the dry acetic acid? It is the propionic acid. From dry acetic acid, after the extraction, propionic acid can be produced. Next, what happens if low CO pressure is maintained at flash vessel? What happens if low CO carbon monoxide pressure is maintained at flash vessel? What happens if low carbon monoxide pressure is maintained at flash vessel? So low carbon monoxide pressure in the flash vessel may result in the loss of carbon monoxide ligands and the precipitation of insoluble rhodium species such as RHI3. That means at low carbon monoxide pressure, the catalyst, the rhodium-based catalyst will be decomposed and we will lose the CO ligands and the insoluble part of this RHA3 will be precipitate. Okay, so that will decrease the effectivity of the catalyst. So this is that is why high pressure is maintained. Next, what happens if methanol carbonylation process produces huge amount of water? What happens if methanol carbonylation process produces huge amount of water? So water, if huge amount of water is present in the reaction, water inhibits the synthesis of methyl acetate and dimethyl ether. Okay, so if less amount of water is present, then so 10 to 15% of water must be retained in the process to maintain the stability and solution of rhodium catalyst. Okay, so if less amount of water is present, then what will happen? Methanol will react with acetic acid and will produce dimethyl ether. And water. Also, this methanol can react, can produce by decomposition so this is DME, dimethyl ether, and this is methyl acetate. Okay, so these two reactions should not happen. That is why huge amount of water or 10 to 15% of water is required. Next, CSTR is used in Cativa acetic acid process. True or false? CSTR is used in Cativa acetic acid process. True or false? So, CSTR is continuously stirred tank reactor. Okay, this is used in Monsanto process, but in the Cativa process, physically stirred reactor is used. That is why it is false. Next question. What are the construction materials used in acetic acid production? So the corrosion resistant construction materials are needed. Corrosion resistant construction materials are needed. So these are Hastelloy C, titanium, and some exotic materials. Okay, so mainly titanium is used. Mainly titanium is used. Next question, explain the reactions involved in hydroformylation of propene. Explain the reactions involved in hydroformylation of propene. So this propene reacts with clean gas, that is the hydroformylation, produces N-butyraldehyde, that is CH3, CH2, CH2, CHO. This is N-butyraldehyde. And the next one is isobutyraldehyde. That is isobutyraldehyde. Okay, so these are the two reactions happen when propene is hydroformalized. Formalized. Next, what is the use of isobutanol? What is the use of isobutanol? So, isobutanol is used as solvent. Okay. Isobutanol is largely used as solvent. Next question. What is the name of the plasticizer alcohol produced from butyraldehyde? Okay. What is the name of the plasticizer alcohol produced from butyraldehyde? The answer is 2-ethyl hexanol. 2-ethyl hexanol. Next, what type of oxo alcohols used in detergents? What type of oxo alcohols used in detergents? The answer is C11 to C17. These chemicals are used for detergents, or these type of oxo alcohols are used for detergents. Next, PVC is a stiff plastic. PVC is PVC is polyvinyl chloride. Is a stiff plastic. Is it true or false? The answer is true. PVC is a stiff plastic. Next, name of the most prevalent plasticizer and how is it produced? Name of the most prevalent plasticizer and how is it produced? So the most prevalent plasticizer is di-2-ethyl hexyl phthalate. Okay, di-2-ethyl hexyl phthalate. It is also known as dioctyl excuse me, phthalate. That is DOP. And how is it produced? This is the first question. The second question answer is 2-ethyl hexanol reacts with phthalic anhydride produces DOP. Okay, so these two reactions produces DOP. And in the in this plasticizer reaction also you can see that first from N-butyraldehyde 2-ethyl hexanal is produced. Then after dehydrogenation 2-ethyl hexanol produced. Okay. So now this 2-ethyl hexanol reacts with phthalic anhydride and produces dioctyl phthalate, that is DOP. Okay. This is the reaction. If you could write with the structure or with the chemical formula, then the answer will be much more impactful. Okay, much more impactful. Okay. Next, alkyl sulfates are cationic surfactants. Alkyl sulfates are cationic surfactants. Is it true or false? The answer is false because alkyl sulfates are anionic surfactant. Okay. Next, what are the temperature and pressure conditions maintained for equilibrium conversion in hydroformylation reaction? What are the temperature and pressure conditions maintained for equilibrium conversion in hydroformylation reaction? What is the temperature and pressure conditions maintained for equilibrium conversion of hydroformylation reaction? The answer is not low, rather it is low or high. That is low temperature and high pressure. For good equilibrium conversion, low temperature and high pressure is maintained. So low temperature means around 300 to 600 Kelvin, and high pressure means 100 bar. That will give more than 30% conversion. Next, what is the ratio of hydrogen carbon monoxide propene in hydroformylation reaction? What is the ratio of hydrogen carbon monoxide and propene in hydroformylation reaction? The answer is 1:1:3. Okay, so this is the next question. What is the thermodynamically preferred product in hydroformylation reaction? What is the thermodynamically preferred product in hydroformylation reaction? The answer is isoaldehyde. Isoaldehyde is a thermodynamically preferred product in hydroformylation reaction. Next, what is the first catalyst used in hydroformylation reaction and what is the catalytic stability pressure of it? What is the first catalyst used in hydroformylation reaction? So, the catalyst is cobalt, hydridocarbonide. Okay, so its structures is HCO, that is cobalt, and 4 carbon monoxide. And it is the first question, and the stability pressure is 200 to 450 bar. Okay, this is the extremely high pressure for catalytic stability for this particular catalyst, which was first used in the hydroformylation reaction. Next, what is the stable catalyst used in hydroformylation reaction? Latter. So, what is the catalyst used, stable catalyst used in hydroformylation reaction? The stable catalyst is tributyl phosphine substituted cobalt carbonyl catalyst. Tributyl phosphine substituted cobalt carbonyl catalyst, that is HCO, 3 moles of carbon monoxide, then PnC4H9 whole 3. This is the tributyl phosphine. Okay. Next question. Write the correct order of catalyst activity in hydroformylation. Write the correct order for catalyst activity in hydroformylation reaction. The correct order is this. Okay, so based on the catalyst activity, rhodium is highly active, then comes cobalt, then ruthenium, and then manganese. Okay, so for hydroformylation, this is the order. Next, what is the rhodium based catalyst used in hydroformylation reaction? What is the rhodium based catalyst used in hydroformylation reaction? What is the rhodium based catalyst used in hydroformylation? So rhodium based catalyst is rhodium complex with Triphenyl phosphine ligand. Triphenyl phosphine, that is TPP ligand. Okay, so this is HRHCO, then PPH3 whole. This is the triphenyl phosphate. This is the one, and second one is the water soluble ligand is TPPTS. Its full name is, so here the rhodium complex with TPP ligands, here the ligand is water soluble. So that is triphenyl phosphine M trisulfonic acid trisodium salt. So that whole together is TPPTS. This is used. This is the catalyst name. This is water soluble and the first one is not water soluble. Next, write the side reaction for hydroformylation. Write the side reaction for hydroformylation. The answer is hydrogenation of alkenes and 1-hexene to 2-hexene. So both of them are the side reaction for hydroformylation. Okay, not this dehydrogenation of alkanes or hydrocracking of aldehydes. Okay. Next, selectivity of rhodium catalyst towards normal aldehydes is lower compared to cobalt in hydroformylation. Selectivity of rhodium catalyst towards normal aldehydes is lower compared to cobalt or hydroformylation. This is false because rhodium catalyst can produce more aldehydes, okay, than cobalt catalyst. So that is false. Next, which catalyst promotes double bond isomerization? Which catalyst promotes double bond isomerization? The answer is cobalt. Cobalt promotes significantly double bond isomerization. Next, what are four steps used in low pressure hydroformylation? What are four steps? What are the four steps used in low pressure hydroformylation? So, the first step is the reactor, then gas liquid separator, then stabilizer, then aldehyde distillation. Okay, these are the four steps of low pressure hydroformylation reaction. So here you can see the diagram flow chart. That reaction, first one is a reactor, start tank reactor, which is at significantly low pressure, that is just 20 bar, and cobalt catalyst is used here. Okay. Next, the alkene and synthesine gas, the propene and syn gas, that is Cu and H2, is purified, and catalyst is particularly poison sensitive. Through asperger, the gaseous reactants are delivered into the reactor. Okay, first one is the reactor. Then catalyst is dissolved in the product. Rhodium remains in the reactor but for a brief purification cycle. The gaseous effluent of the reactor is passed via the demister. This is the demister, that the fine droplets of catalyst induced where the fine droplets of catalyst induced infused in the product gases are removed and returned to the reactor. Okay. Next, from the demister pass into the reaction products and the unconverted propene. are delivered to the gas liquid separator. Okay, then this is the second one. Then this goes into the stabilizer column where residual propene is removed from the liquid reaction products, which are then further purified by the distillation column, aldehyde distillation column. Okay. So from the stabilizer, some of the parts gases or unreacted propene are recycled, and from the bottom, the product is collected and it is separated in isobutyryldehyde and N-butyryldehyde. These are the four steps. Next question. If we use water-soluble rhodium-based catalyst in hydroformylation, then separation is simplified. The answer is true. If water-soluble catalyst can be used, then the separation will be simplified. Next, stripper column is used to separate unreacted propene. Is it true or false? Stripper column is used to separate unreacted proton. The answer is true. Next, how the catalyst is separated in Exxon hydroformylation process. So, first this cobalt-based catalyst can react with Na2CO3, sodium carbonate. This will give cobalt and sodium salt. Okay. This cobalt sodium salt is washed with sulfuric acid. Then it can produce again our desired catalyst, and sodium sulfate will be precipitated. Okay, so this is how we can separate the catalyst in Exxon hydroformylation process. Next question, explain the steps in Exxon hydroformylation process. So here first is reactor, then flash vessel, then cobalt removal, then wash column, then catalyst regeneration, then catalyst absorber. So in the flow chart only, that means when this type of question comes, you have to write the flow chart. Okay. So you can see that here alkenes, that is propene and catalyst complex and syngas is coming to the reactor. Then it goes to the flash vessel where gaseous part and the liquid part are separated. Then it goes into the cobalt removal from where this catalyst complex is separated with the formula we have shown with sodium carbonate reactions and followed by the sulfuric acid mixture. Then it goes to the top product goes to the this section, and from where this off gas is separated, right? And from this the bottom product comes into the catalyst regenerator wash column where water is given. Okay. Then it goes into the catalyst regeneration where the H2SO4 is added, and you know that catalyst is recovered from the top and aqueous sodium sulfate is precipitated at the bottom. So this catalyst is absorber. So now this is the absorption column where the catalyst is absorbed, right? So this is how the reaction, the hydroformylation reaction Exxon process is done. Okay, so it is written everywhere in the bottom. Alkene, recycled and makeup catalyst and synthesis gas are fed to the hydroformylation reactor in a start tank or loop reactor simultaneously. Then after passing through the flash vessel in which the gas is separated, the crude product is treated with an aqueous sodium carbonate solution in countercurrent flow. Then this cobalt complex forms a sodium salt which is water soluble. After water scrubbing in the wash column, the organic phase and aqueous phase containing the sodium salts remain. And here the crude aldehydes are transported for distillation. The surplus alkenes are recovered and returned to the reactor for cycling. Okay. This is how cobalt is generated. The hydroformylation reaction happens. Next, low pressure hydroformylation process produces what? Low pressure hydroformylation process produces alcohol, not aldehyde. So till now we have studied about the aldehyde production or isoaldehyde production. Now we are seeing that it produces alcohol. Next, what is the reactant for low pressure hydroformylation using cobalt? So alkene is there, then obviously syngas is there, but the hydrogen amount is very less. So hydrogen 4 syngas is there. Okay. Next, Hydrogen-rich gas is introduced in the first reactor in low-pressure hydroformylation using cobalt. Is this true or false? So, if we go to the slides, you can see that here, the first reactor, hydrogen-poor syngas is added, but in the second reactor, hydrogen-rich syngas is added, right? So, as per the questions, hydrogen-rich syngas is introduced in the first reactor. It is false. Okay. Next, what chemicals can be produced from ethene oligomerization? So, in by ethene oligomerization, C4 to C18 alkenes can be produced. C4 to C18 alkenes can be produced. Next question and the last one. Which catalyst is used for ethene oligomerization? So here the answer is Ziegler type catalyst. Okay. So that is from my side. So you have to go through all the lectures very carefully. This is the shock process of ethene oligomerization, which is important. That is shale higher olefin process. You will see the process involved. So here you can see if we use plain alkenes or single chain alkenes, then only the shale shock process produces higher conversion. Okay, next. This is the shock process or oligomerization process, from where oligomerization of ethene results in one alkenes with chain length ranging from C4 to C40. Okay, so C4 to 8 constitutes 40% of general distribution, C10 to C18 comprises 40%, and C20 plus alkenes constitutes 20%, right? Then you will learn about the distribution. This is the metathesis reactions where metathesis of propene produces ethene and butene. Okay, ethene and butene produced by propene. Okay, this is a thermoneutral reaction. So this is the metathesis reaction you are seeing, right? The propene production is higher, 60 to 70%. Okay. This is the metathesis reactions where ethene and butene are going to the reactor at very high temperature, that is more than 530 Kelvin, and then it goes to the ethene column, from where ethene is purged and some of the ethene is recycled, and the product goes into the propene column, from where top product is propene and bottom is the butene, or higher number of alkenes are purged. Okay, right? So this is the catalyst that is happening, 1 butene to 2 butene, and the output is cooled and ethene is extracted for recycling. You are seeing here. In the propene column, polymer grade propene of high purity is obtained by separating recycled butanes. A small portion is purged to eliminate butanes, isobutanes, and heavier substances. Okay, so all the butanes are separated from this bottom product of the propene column. This is a comparison of all the processes. This is the mechanism of the catalytic cycle for the oligomerization of ethene. Okay, so this is the metathesis process, how the double bond isomerization happens, how the metathesis happens. Okay. right? So this is the shop process. That is the metathesis process. This is the shop process. Okay, everything is happening. The isomerization also happening. The metathesis also happening. Okay, so this is the reaction. You need to remember the flow chart. I mean, and this is done. Okay, so this is from my side. So I hope you find this session helpful, and you will go through the everything is said or everything is written in the slides also. If you carefully listen the lecture also, you can also solve the assignment. So carefully go through it, and till then, goodbye.